time to continue. Almost stretch yourself and then the final stretch for the first day, okay? So, mixer fraction. We have introduced mixer fraction, and we're going to talk about Burke-Schumann solution. So what's nice is that the mixer fraction then, so let's think of a non-premixed flame like I showed you earlier. You have, in certain regions, you have pure fuel, mixer fraction is 1. In certain regions, you have pure air, mixer fraction is 0. And then something in between, the mixer fraction tells you what it is. And the Burke-Schumann solution really gives you, assuming one-step global reaction infinitely fast, but it gives you then the solution, I mean, it gives you the local constant or local mass fractions of all species as functional mixer fraction. So that's already a very powerful concept. So here we start out, I mean, these are two equations we had before, and they describe how fuel and air, fuel and oxygen, are, how they depend on mixer fraction if it's not burning. So this basically means I take my cigarette lighter and I just turn it on, or here my torch here, my Bunsen burner. I just turn it on, gas is coming out, and I could measure now, and I could locally measure oxygen and fuel and mixer fraction, or compute mixer fraction, and the solution looks like this. So it's just a linear function here of mixer fraction. And oxygen here, so this is pure air, and so the mass fraction here would be 23%, as in pure air. And then here, the fuel mass fraction would be 1. I mean, in my example, but it could also be something else, okay? And, right. And now, of course, we are more interested in trying to see what happens when it burns. And that is then shown here. I mean, this is the definition of mixer fraction. And now we assume, first of all, we look at what happens when mixer fraction is smaller than stoichiometric. And we said earlier, if we're in the lean region, then the fuel will all be consumed, and there's some oxygen left over. And so, you know, in this equation, I can just say, in this region then, the fuel must be 0, and then I can solve this equation here for YO2, right? And then I get YO2 as function of Z. This part here is nothing else than Z stoichiometric. We introduced that, and then this is what we get, okay? And so you see, this shows you YO2 burnt as function of mixer fraction. And you see, again, it's linear. And this is just for lean region. Okay, I can do the same for the rich region, where then oxygen is 0, and I can, you know, do the same thing and determine the fuel mass fraction. And then now I know fuel and oxygen, and I can also then, assuming I have a hydrocarbon, I want to know what is CO2 and H2O. And that comes then from, I mean, these are not, I mean, here I just started out with this equation, but CO2 and H2O are not in that equation. So what we do here is we use now the element mass fractions. I know before it burns, I have carbon, hydrogen, and oxygen, you know, depending on mixer fraction. And then after it burned, I have the same amount, the same number of, let's say, hydrogen atoms, but now they're in water and not in the fuel. And so that's what we do here. We define the element mass fraction. Remember, this was the element mass fraction equation, and now assuming we have hydrocarbon fuel, these are, so this is the carbon element mass fraction. It just comes from the fuel. Hydrogen just comes from the fuel. Oxygen just comes from the O2. And then after combustion, again, I can do the same thing. Carbon comes now from fuel and from CO2. Hydrogen is from fuel and from H2O. And oxygen here is from O2, from CO2, and from H2O. Okay? But now these have to be, before and after combustion, they have to be the same. So I can just say this here has to be equal to this. And these I know, everything here I know. And here the only unknown, I know this also, I computed this earlier. The only unknown is this YCO2. So I can solve this for YCO2. I can do the same thing here with YH2O. This one actually I don't even need. And so, so this is what I get. For lean mixtures, for rich mixtures, I get this. And then these here depend on YCO2 stoichiometric. I can get this from, anyways, I mean, this stoichiometric is then given in this form, comes from the coupling function. Okay, here from this equation. Okay, so right, and now I have all species as functional mixture fraction, and I plot this here, and this is how it looks like. This is stoichiometric. In the lean, I have oxygen goes to 0. Oxygen in the rich is 0. In the rich part, fuel goes from, let's say, 1, or the mass fraction in the fuel stream, all the way to 0 at stoichiometric, and then it's 0 in the lean region, and then this is water, and this is CO2. It's all linear, okay? So that's really interesting, because that means if I want to know, you know, what happens in this flame I showed you earlier, let's say it's a laminar flame, or a turbulent, doesn't matter, but let's say it's a laminar flame, I want to know what happens. I only need to solve an equation for mixture fraction. I said earlier it's a linear equation and it has no chemical source term, so it's very easy to solve. That gives me the mixture fraction field. I know, you know, this region mixture fraction is 1, here 0. I know how it changes from 1 to 0 once I solve the equation. And now I know everywhere what the CO2 mass fraction was, H2O mass fraction, and so on. Okay? We made a lot of assumptions here. But, so this is called the Birk-Schumann solution, is from 1929 or something. So it's quite old, but again, yeah, very powerful. That's one of the easiest, I mean, what I just said is one of the easiest combustion models for premixed, for non-premixed combustion. Okay, and what do we assume again? We assume one-step global reaction, and we assume infinitely fast chemistry with full conversion to H2O and CO2. And that's why you see here, at this point, infinitely fast chemistry means, you know, fuel and oxygen, they're consumed at the same time. And what's interesting here also, it means that the reaction zone, where's the reaction? Reaction zone is the region where chemical reactions happen, okay? Where's the reaction zone? The reaction zone, where do reactions happen? Reactions cannot happen here. Why? Because there's no oxygen, you know? Reactions cannot happen here because there's no fuel, okay? So reactions only happen if you have both fuel and oxygen at the same time, okay? And that is only exactly here. And as soon as you get a little bit of oxygen and fuel at the same time, fast chemistry makes it go away, okay? So that's why the reaction zone in this model is infinitely thin, okay? Because, you know, infinitely fast chemistry means you can never have fuel and oxygen at the same time. It's not possible, okay? Because it will react infinitely fast and consume itself. And, I mean, that's interesting because in non-premixed flames, or let's say, you know, infinitely fast chemistry is correct, then it really means, you know, there's no reactions here, no reactions there. All reactions happen in a single infinitely thin sheet. And because in non-premixed combustion, chemistry is usually relatively fast, is often relatively fast, not infinitely fast, but very fast compared to mixing, it means that this reaction zone, I mean, when it's infinitely fast, the chemistry, it's infinitely thin. When the chemistry is still very, very fast, this is very, very thin, okay? So that's why in typical combustion, non-premixed combustion systems, the reaction zone is very thin. And that's what you saw, you know, take a cigarette lighter if you have one, and look at the blue sheet that you see. And you see it's very thin. And outside of this, the basically no chemical reactions. Of course, you know, you form soot, that happens outside. But in principle, fuel and oxygen are consumed, you know, in a very narrow region, and, you know, without fuel on one side, without oxygen on the other side, there are no reactions, okay? So that's an interesting outcome of this. Okay, any questions about this before we go to the, I think that's the last slide here, the next section. No? Then okay, this was mass balances. Now we're going to talk about thermodynamics. And again, we start very simple, same thing. I mean, just instead of introducing, you know, mass fraction, we introduce internal energy or whatever. So again, I'll try to do this fast. So, but what we want to do is, you know, we introduce a few concepts or a few terms. Then we talk about first law of thermodynamics, flame temperature, and then we talk about equilibrium. So first law of thermodynamics deals with a balance of energy. Here, U is internal energy. This is a change of internal energy, and then we have work, which is here is PDV work or you know, volume change work, and then dQ here is heat transfer. Okay, and then the first law says, I mean, if you define a system, the change of the energy inside the system is equal to the fluxes of energy across the boundaries, you know, by heat transfer, by work, and then also with mass flux, which would introduce the enthalpies. So that's internal energy. We define the enthalpy as U plus PV. You know this. Now for an ideal gas, we always assume here ideal gas. PV is equal to RT. And so if I introduce this here, then you see that the enthalpy is U plus RT divided by a molecular weight. And for an ideal gas, the internal energy only depends on temperature. I mean, in general, in general, thermodynamic quantities always depend on two other thermodynamic properties. That's what the state principle tells you. But internal energy depends only on one, and that's the temperature. Okay, it's independent of pressure. And while the enthalpy here is the pressure in its definition, because PV is RT, you see enthalpy also depends only on temperature. That's important, actually, that you know, enthalpy and internal energy only depend on temperature, not on pressure. Okay. We talk about multi-component mixtures, so each component has its own internal energy or enthalpy, and so the total enthalpy or specific enthalpy here of a system is, you know, determined from the sum of the individual enthalpy here times the mass fraction. Okay, that's obvious. This we just said already. Now this is an important aspect here. So the enthalpy is equal to, well, U times RT. We had this already. But then the question is, how do I actually determine the enthalpy? I mean, I need an equation of state. And the equation of state is from the definition of the specific heat, Cp. We just say, we define the specific heat as dH by dt at constant temperature, right? dH by dt at constant pressure, sorry, okay? That's the definition of specific heat. And then because the enthalpy depends only on pressure, we can say a change in enthalpy is Cp times a change in temperature, okay? So that is the equation of state. And this now I can integrate. I mean, it's all trivial, but there's an important point coming. I can integrate from some reference enthalpy to and reference temperature to a given, enthalpy and temperature. So I do this, and then I get HI minus HIRF is equal to the integral of CPdT. Okay? Then sometimes in thermodynamics class we assume now always CP is constant, then we can directly integrate it. Here we cannot do this, or we'll see later a case where we do this. But so we need to keep this integral. But you have HI is HRF plus this integral, and that's very important. Why? You have the enthalpy has two different parts. Okay, has this reference part, and it has this temperature-dependent part. What does that mean? It means you have a species that has a formation enthalpy. That's the enthalpy the species has to be formed at that state, let's say. And then also you have a part that depends on the temperature. Now, when you have a chemical reaction, you consume one species and you form another one. You consume H2 and O2 and you form H2O. Now, it so turns out that the enthalpy to form, the chemical enthalpy to form water is much lower than the enthalpy to form H2 and O2. Okay? Which means, in the beginning, I have H2O2, I have a lot of chemical energy, and then I convert it to H2O, and then I have very low chemical energy. Okay? This, first of all, this tells us a system always wants to go towards the lowest energy, right? I mean, you have to listen to us the whole day. It's tiring. You go home later on, you come to your room, there's a bed, and immediately you fall in your bed. Lowest energy. That goes just by itself, okay? Or after you partied tonight, whatever. But but tomorrow morning, getting out of the bed, going to a higher state of energy, that's very, very difficult. Okay? So everything always goes to the lowest state of energy. Take the laser pointer, it has potential energy, and the only reason why it keeps the potential energy is I put a constraint. I hold it in my hand, okay? If I let go, it will immediately go to the lowest energy, which is on the ground, okay? I will not show this to you now, but you know how it happens. So same with chemical reactions. You have species that have high energy, and you put them together, they don't want to be there. They want to be at the lowest possible energy, and the transition to the lowest possible energy, it's spontaneous. It goes by itself, okay? Now, for chemical reactions, sometimes it takes a long time, but we know ultimately it will happen, okay? So what happens then is that you had high energy in the beginning, you do the reaction, and then you have low energy. The first law tells us energy doesn't go away, okay? So it must have appeared in a different form. Where did it appear? It appears in the second term, okay? So this is what I have as part of this and this. In the beginning, this is very high, and this is very low, because low temperature. Now I burn everything. Now this is very low, which means this must be very high, okay? So combustion is the process of converting chemical energy into sensible energy, temperature. And this equation, has this. So think about this in terms of, this is the chemical energy, this is the thermal energy, okay? So the equation has this transition from one to the other. Now, the reference enthalpy can be defined, whatever, and sometimes in different tables it's defined differently. It could be here typically something like 298.15. It doesn't matter. I mean, it just is a definition, but these two, they need to be consistent, this temperature and the value. Now, this just shows the same thing here for enthalpy, molar enthalpy, same thing here, molar CP and so on, not very important, except maybe here. You have the CP for one species, and then multiplied with mass fraction, sum over all, gives you the mean CP of the mixture. And then, how do you determine these enthalpies? I mean, you determine them by just integrating this equation. For this, you need to know the CP, and the CP is usually stored in tables. You know, there are tables that tell you this. Now, one thing that's interesting is that you need to have a consistency between different species. You need to have a consistent definition of the reference for different species. And when we determine these chemical energies, we think of it as a box of Lego. You know Lego? Is this, yeah. So you have the little blocks, and you take the little blocks, maybe these are the atoms, right? And then you put together molecules, you know, from the box. And so each of the blocks needs to have an independent definition. Each color, let's say, of block, Lego block, has to have a definition for the point of zero energy, okay? And that's what we do here. We say for hydrogen, oxygen, nitrogen, and carbon, we need to define a zero value, and we say the molecules, hydrogen molecule, oxygen molecule, nitrogen molecule, and solid carbon, they have zero enthalpy. That's just a definition, arbitrary definition. It's very helpful. Why do we do it this way? Because, you know, when we do experiments, then at room temperature, you know, these are stable. I mean, you know, hydrogen, oxygen, nitrogen at room temperature, you know, they would appear in gaseous form. Carbon at room temperature, pure carbon, is solid, is basically coal or graphite or whatever. So, right. And, okay, that's what I said earlier. Then typical reaction products have the negative energies with respect to this, you know, because otherwise we'll say that it wouldn't be true. So we have so how do we compute these? Typically, you don't integrate, as I said earlier, or actually you do, but we write these in terms of power laws, and then we have coefficients here. So this is an expansion, you could say. We have coefficients here, and these coefficients are stored in tables. So CP depends on 1, 2, 3, 4, 5 coefficients, here fourth order polynomial, and then power law, I should say polynomials, fourth order polynomial, and then actually you can integrate this, CP dt, you can integrate this, you get A1 times T and so on, and you see that's exactly what you have here. So HM is just the integral of this equation, you know, 1/2 T squared, you see I have a T here, brings to the other side. So these are the same, and then you get one extra is the integration constant. So that's basically pretty much the reference enthalpy we mentioned earlier. And then the entropy, you know, is written in a similar way where, you know, it's a little more complex here. But one other thing is interesting. What's interesting about the entropy in contrast to the enthalpy? Sorry? It depends on pressure. Yeah, you're too fast. It depends on pressure also. Entropy depends, I mean, internal energy for an ideal gas depends only on temperature. Enthalpy depends only on temperature. Entropy depends on temperature and pressure. That will become important later on, so keep that in mind. Okay, so this is how these tables look like. Typically, the coefficients here, they are tabulated in two sets. One for temperature below 1,000 Kelvin, and one for here below 1,000 Kelvin, and one for temperature above 1,000 Kelvin, just to make it more accurate. So these tables you find on the web, and they usually come with chemical mechanisms. So then, let's look at a chemical reaction. First law says du is dq plus dw. Then we, I mean, usually when you have constant volume processes, it's good to look at internal energy. When you have constant pressure processes, it's good to look at enthalpy. In combustion, very often we have constant pressure processes, which is why we very often use the enthalpy instead of the internal energy. So H is U plus PV. So DH is DU plus, and then product rule, VDP plus PdV. And you see DU plus DU is DQ plus or minus PdV, DU minus PdV plus PdV. So this goes away. And then, oh no, this goes away. We look at a constant pressure process. So this is 0 also. And that means DH is equal to DQ. Okay, so the change in the enthalpy, it gives you the heat release. Basically, that's what this says. And then we define here the heat release basically as the heat of combustion. We say the heat release is equal to the change in the enthalpy from reactants to products, or the chemical enthalpy from reactants to products. And so this is written like this. So here with the stoichiometric coefficient, which is positive for the products, negative for the reactants. And so if I have a reaction like this, CO plus 3H2, so CH4 plus H2O, and I want the reaction enthalpy, then you see it's the enthalpy of H2O plus CH4 minus that of CO minus 3 times that of H2. Okay, that's the reaction enthalpy, evaluated at one constant temperature, let's say at the reference temperature. So, how do I measure this? How do I measure now the reference enthalpy of a species? As I said, we look at it like a Lego system. I do a reaction here. So, for example, I want to know the reference enthalpy here for CH4. Then I take pure carbon and 2H2. I convert them here to CH4, and then I measure the change in enthalpy. I can measure this, and then I write the reaction enthalpy of this equation is the enthalpy of CH4 minus that of solid carbon minus twice that of H2. But we said these are defined to be 0. Okay, so the measured change in enthalpy is just the reference enthalpy, and same thing for these other ones. Okay, so the reference enthalpy means that's the physical interpretation. The reference enthalpy is the chemical energy of a species with respect to these species. Okay, and it's tabulated. You can look it up, and then you can determine reaction enthalpy, for any reaction you want. You can see if it's exothermic or endothermic, or how much heat is released, and so on. So this here shows different species, and this reaction enthalpy. And again, here you see H2 is 0. That's what we said earlier. H2O is negative. CO2 also must be negative, and so on. So this is just a part in the script I showed you earlier. You can download from our webpage more tables. And probably these are old tables, so some of these must have been determined more accurately today. But for back of the envelope calculation is very useful. And then we can define, from the reaction enthalpy. So reaction enthalpy is basically the enthalpy per mole of fuel that's consumed. We can also write this in terms of mass, and then we call it the heating value. So you have the lower heating value is just the reaction enthalpy divided by the molecular mass of the fuel. That tells you then how much energy do you get by burning 1 kilogram of fuel rather than 1 mole of fuel. And then for hydrocarbons, there's a little peculiarity, which is if you burn it, you get water. Water vapor has more energy than liquid water, the latent energy. So if you burn it and the exhaust is vapor, is water in the vapor phase, then you get less thermal energy than if you condense the water, okay? So that's why we have a lower and an upper heating value. And the upper heating value is just the lower heating value plus the latent heat of the water that is produced. And the water is produced, again, you can look at the element mass fraction of hydrogen in the fuel, because the whole thing is per unit mass of fuel anyways. So the element mass fraction times here converted to hydrogen water mass fraction times the latent heat, per kilogram of water. And that term here, so that makes it very easy to compute this, because these are all constants here except for this. And so that term here is typically, let's say, like 10%. So it's a big thing. And if you take domestic heaters, now domestic heaters are built to use the upper heating value, the higher heating value, by condensing the water. Okay, so you have the exhaust that goes out, and then you have fresh air coming in a heat exchange, in a kind of a heat exchanger fashion. I mean, you have just a chimney, and the chimney has a concentric outer pipe where the air is drawn in and fuel goes out, and while the fuel then is cooled down, you heat up the air, but then the water condenses and is extracted. So they use this, and they play funny games with this. So this here is a so-called condensing boiler. Is a heating system, domestic heating system. And they say here, performance and design. The model is a high-performance compact condensing boiler which provides an efficiency of up to 108%, okay? And that is not bending the laws of physics, which is the first law of thermodynamics. It's just playing games with the numbers. They assume the lower heating value, but they use the upper heating value, okay? And have 2% loss, and then they get 108%, yeah? But it's not bad, good technology. Okay, good. So this was just introducing a few terms. Now we're going to compute the adiabatic flame temperature. What is the temperature in a flame at complete, or after combustion, at complete conversion? That's the assumption now. And so again, we write the first law. Here, du is dq plus dw. It's supposed to be adiabatic, okay? No heat loss. Then dw is just minus pdv. We do the same thing here. Again, I put this, here, this is the definition of the enthalpy change. And then for du, I write minus pdv. This goes away. It's adiabatic, it's constant pressure. So this also goes away, which means in an adiabatic constant pressure system, the enthalpy stays constant. Okay, that's why, we talk about constant pressure system, that's why it's so nice to use the enthalpy, because it's just a constant. So if you have a flame like this, like I showed you earlier, if I just look at, in the beginning of combustion or after combustion, enthalpy is always the same. The only difference is, before combustion, all the energy is in the chemical energy, the reference term. After combustion, it's all in the temperature-dependent term. Okay, so the unburned enthalpy is equal to the burned enthalpy, and the enthalpy is written as the sum of Y times H over all species. Okay, so that's the equation we're going to consider. And then now the enthalpy is the reference term plus the temperature-dependent term. And I plug this in here. So here I have two terms, unburned and burned. No? Yeah, two terms. Now I plug this in, I get 4 terms, right? I take the reference terms on the left-hand side, unburned and burned, and then the temperature-dependent terms on the right-hand side. So that's the equation we're going to start out with. And then, so you see here, this is the burn temperature. That's what we want to know. The specific heats we defined earlier. That's the equation again. And now, first, we're going to look at the term here on the left-hand side. And then after that, we're going to look at the term on the right-hand side. Okay? So let's start here with this underlined term. For this, you see, I have the mass fraction burned minus unburned for all species. And of course, I can relate each one of these with a coupling function, to just the change of the fuel mass. And the fuel mass, we know. We know the fuel mass in the beginning, and at the end, fuel mass, at least for lean combustion, fuel is 0. okay? So coupling function helps us here. So that's what we do, this coupling function. I integrate it, I get this. I just put here this coefficient on one side, okay? And I relate everything to the fuel. And now, so this is just for one species, right? For I multiply this here, you see? I multiply this with the reference enthalpy and I sum over all. Multiply this with the reference enthalpy here and I sum over all, okay? And then I get this term, now expressed just by the fuel. And you see, this is just, this here is just a reaction enthalpy. I just showed you how to determine this from the table. And then this here is fuel unburned, that's our initial condition. And this fuel burned is 0, so I know this term. I can evaluate this term quantitatively. Okay? So this I just said, I mean, this is a reaction enthalpy, call this heat of combustion, whatever. One thing that is important here, maybe to note, is that the heat of combustion depends, I mean, it's not as reference condition, maybe it depends on the temperature, but we want to say the heat of combustion should be independent of temperature, so we can evaluate it here at the reference condition. And then the other simplification we make is we say, that's not a simplification, it's just a definition. We say the reference temperature should be the unburned temperature, and here that's the assumption we make. We say the specific heat should be constant, okay? So that we can integrate the right-hand side. And we want to say, I mean, there's some arguments here for why, but we want to say, I mean, you know, at least for premixed combustion, it's mostly nitrogen anyways. And so we want to say Cp is 1.4. And then I can integrate the right-hand side here. If the Cp's are constant, I can integrate the right-hand side. I just get Cp times Tb minus Tref minus Tu plus Tref. Reference temperature goes away. And what's left over is just Cp times Tb minus Tu. This is the term for the left-hand side we evaluated earlier. And you see, now I can solve this here for Tb minus Tu. And I get this here on the right-hand side. This was the reaction enthalpy, the unburned fuel mass fraction, and then and this here comes from the global reaction. Okay, so we have an analytic expression for the temperature, and now I can do this. So this was for lean condition. Okay, I can do the same thing for rich. Now reference everything to oxygen. I assume oxygen in the burn is 0 and so on. And so I get this here for rich conditions. And for stoichiometric, there must be the same. So we can test this out. Let's take a stoichiometric methane-air mixture at 298 Kelvin. And so first, this global reaction. The heat of reaction is given here is HCO2 plus 2 H2O minus methane minus 2 oxygen, but oxygen enthalpy is 0, so that doesn't appear. You look in the table I showed you earlier, 800 something kilojoule per kilogram, and then this is for stoichiometric condition. This is the fuel mass fraction I mentioned earlier, is about 0.055. So this is the fuel mass fraction, Cp is 1.4, here the molecular mass of methane, and then I can plug all this in and I get 2,261 Kelvin, and if you get this from more detailed thermochemical data, something like 2,225, so you see the error here is relatively small. Now, there's a little trick. We assumed Cp is constant, we assume it's 1.4. You could also assume a different value, and then you get a different temperature, right? I mean, it works well with 1.4, but anyways, I mean, again, it gives you something a good, back of the envelope way to calculate the burn temperature. Right, here's another thing that's interesting. Earlier on, we looked at the Buck-Schumann solution, and we said it gives us all the mass fraction as function of mixture fraction. We didn't talk about the temperature. I mean, there's also an energy equation. We don't want to know what the temperature is also. But this here allows us now also to do the same thing for temperature, because for any given fuel mass fraction, I can tell you now what the temperature is, right? And so we can, because we know the fuel mass fraction, as function of mixture fraction, I can just plug this in here, and then we get the temperature also as function of mixture fraction. So that's what we do here. So this is you need new batteries, but on the top left, you see the temperature, adiabatic temperature for lean condition, on the right for rich condition. And then these are the relations we had earlier for Y fuel unburned, Y O2 unburned as function of mixture fraction. I can just plug this in there, and then I get TB as function of mixture fraction. One more thing, what is the unburned temperature? If I have a non-premixed flame, the fuel temperature and the oxidizer temperature, it could be different, right? For example, in a diesel engine, the air is compressed, is at high temperature, maybe 800 Kelvin or 900 Kelvin, and the fuel is liquid injected at room temperature or whatever. So these are different. So that's why we say the unburned temperature also depends on mixture fraction. It is just a linear. It's just a linear function between the fuel temperature and the oxygen temperature. That's what this is. So I can plug this in also up here, and then you know, this just shows the expressions that you get, but they are just linear relations. And you know, here all the Q stuff and so on, we just computed this. And then this is how it looks like. No surprise, it looks like the CO2 and the H2O profile, but it's quantitative now also. The stoichiometric temperature here we can compute, and then it's just linear profiles left and right. And this complements then the Buck-Schumann solution we had earlier. Now we have an expression for all species and for the temperature as function of mixture fraction. But again, this assumes infinitely fast, irreversible one-step chemistry. Irreversible means full conversion, okay? There's no fuel and no oxygen left. It's all products at the end. This just shows a table for different fuels and the adiabatic temperature. And you see, you know, they're all around 2000 something, but they can be different. And you see double bond gives you higher temperature, triple bond. Also double bond here would be ethylene is a little higher, and a triple bond here for acetylene is yet higher. But here all the saturated ones, propane, ethane, and methane, they're very similar. They're not very different, okay? So that's something maybe to remember, you know, the stoichiometric temperature is maybe 2000. I always remember methane is 2222, okay? You know, that's something one can remember. Okay, now we said this is infinitely fast, irreversible chemistry, but in reality, chemistry is not irreversible. You know, at the point where you had only, I mean, let's say I have just H2 and O2, and I convert everything to H2O. At the point where we have only H2O, the entropy would be so low that, I mean, the potential, the chemical potential would be so high that, you know, this wants to form H2 and O2 again. I mean, there's no chance, there's not one water which will split up and form H2 and O2 again, okay? So that's the chemical equilibrium. So that's what we want to compute. We want to compute the chemical equilibrium because of two reasons. I mean, first of all, that's, you know, a little closer to reality compared to what we just discussed. And secondly, also, as I said earlier, the equilibrium always gives you the direction where you move. The world goes to equilibrium, okay? So every chemical reaction always tends towards equilibrium. How can you make it, that's it. I mean, and you can't make it go the other way, really. I mean, what you do is you change the conditions. If you want to make it go the other way, you have to change the conditions so that the equilibrium tells it you have to go the other way, okay? You can make it go faster to equilibrium by increasing, maybe temperature, but that might change the equilibrium also. But how else can you make a reaction go faster to equilibrium? Sometimes reactions are very, very slow, and you want to have them faster. Yeah, you could increase the pressure. That could make the, as we see later on, it could also make the reaction slower or go the other way. A catalyst, right? Catalysts do exactly this. They make reactions go faster, but they do not make them go the other way, okay? So for example, in combustion, we form a lot of NO. And then in automotive catalyst, you remove the NO. I mean, the reason why combustion makes NO is because this is, the equilibrium wants to have NO. But the catalyst, obviously, it removes the NO. So it goes the other way. Why is that? No answer at this point. We'll see later why this is. Okay, so equilibrium tells you, you know, just where things go after a very, very long time. But equilibrium doesn't tell you how fast it takes, how fast it goes there. So that's what here Professor Zarate tells you in the mornings. Chemical equilibrium is sometimes a good assumption, sometimes a bad assumption. It's a good assumption for hydrogen diffusion flames, where equilibrium, you know, is in all regions is not so bad. For hydrocarbon flames, it's an okay assumption for lean conditions, but for rich conditions it's not, because hydrocarbons, you know, they like to form the equilibrium for hydrocarbons under rich conditions is that you get very large species or a lot of very large species like soot and so on, and you know that kinetics tells you that doesn't always happen like this. And so it overpredicts intermediates such as CO. Okay, so in order to talk about equilibrium, we need to introduce the Gibbs free energy. In order to introduce the Gibbs free energy, we need to introduce the entropy. The entropy, we saw it earlier already. If we want to compute the enthalpy, we have two terms. The constant chemical term and temperature-dependent term. The entropy has three terms. It has the constant chemical term, it has a temperature-dependent term, and in addition, it has a pressure-dependent term. And so we write it very often like this, where we say so that we don't always have these three terms. We say entropy is a temperature-dependent term, Si0, evaluated at a reference pressure P0, plus the pressure-dependent term, okay, which is just ln Pi divided by P0. And so, right, so then we have only these two terms, but this here really, you know, has these two terms. Okay, so then introduce the Gibbs free energy. Gibbs free energy is H minus Ts. Gibbs free energy is, you can show this very easily from first law and the Gibbs equation, you can show very easily. That is the Gibbs, so you have a system. That is for, you know, for constant pressure. That is the amount of work that you can extract from that system. Okay, it's the maximum amount of work. So, and that maximum amount of work, so you can G, so H is the total enthalpy you have in the system, but you cannot convert the whole, I mean, according to first law, you could take the whole H and convert it into work. According to the second law, you cannot, okay? So according to the second law, H minus Ts is what you can convert. So that's G. And when G has a minimum, you know, that's when you reach equilibrium, because a minimum means, you know, all the work has been extracted. There's nothing else that can be extracted. So this system is at the minimum energy. Okay, so G is H minus Ts. That's just the definition. And then, of course, you know, I can write it here like this: as the sum of the partial mole number times the partial molar Gibbs-free energy. Okay, and then equilibrium is when this has a minimum, and so when dg is equal to 0, and I can write dg here just from the Gibbs equation as vdp minus sdt plus here a term mu times dn, which, so this here is, or let me say, the Gibbs-free energy is a function, can be written as a function of temperature, pressure, and the mole numbers or the composition. And so this here means basically when dp is 0, no more change in pressure, that's mechanical equilibrium, right? When dt is 0, no more change in temperature, that's thermal equilibrium. And when dn is 0, no more change in composition, that's chemical equilibrium, okay? And so all these three need to be 0 to reach equilibrium, and then the mu factor here, that's what we call the chemical potential. So in order to, so, you know, we have an equation and we say, okay, we want to say, we consider a system which is now at constant temperature and constant pressure, and now we want to, you know, see what the chemical equilibrium, when chemical equilibrium is reached. And so constant temperature and pressure, the first two terms are 0, and then the question is, when is this equal to 0? That's the question. That's when chemical equilibrium is reached. And so first we need to know what is mu. In order to determine the chemical potential, I can write the total differential of the Gibbs-free energy. So if I write this as a function of pressure, temperature, and composition, the total differential is dg/dp at constant temperature and composition times dp, and same for the temperature, and the same here for the composition. Okay? And now I can, this here is the equation of state. I can compare the equation of state, the coefficients, with the total differential. And then you see that mu has to be this partial differential, dg/dn, at constant temperature and pressure, and constant all other species here, right? But g here can be defined as the sum of ni times gi. So you see, I can evaluate this partial derivative here in a trivial way, because dg/dn is just equal to, here is just equal to mu, okay? And then, dg/dn is just gi, and that's what I should say, and that has to be equal to mu I. So the chemical potential is nothing else than the partial molar Gibbs-free energy, okay? Okay, so I can plug this in here. I can say, then in the first equation all the way on the right, I can replace the chemical potential with the partial molar Gibbs-free energy. Okay? And now, partial molar Gibbs-free energy, how do I determine this? It's trivial, but there's a lot of terms writing. Because a G is just H minus Ts. H has 2 terms, and S has 3 terms. So G is 5 terms, right? 4 of these terms just depend on temperature, and 1 depends on pressure. So we define here one term that depends only on temperature is the chemical part of the enthalpy and the entropy, and then the temperature-dependent part of the enthalpy and of the entropy, okay? And then, so we call this mu0. So that's all the temperature-dependent terms in 1, and then the pressure-dependent term, okay? Just to make writing a little easier. And now we can evaluate this. We can say, when is dg equal to 0? So this, nah, I give up. I changed the batteries now. So you can, yeah, no, that's difficult. Yeah, so we want to see when is sum of mu I dni equal to 0 for one reaction. Okay, I consider only one reaction. And so I do a little trick. I multiply and divide this by nu. And then we have dni divided by nu I. Okay? That's, remember when we discussed the coupling function, we said that is the same for all species. That's independent of the species, so I can take this out of the sum. That's the trick. Okay, if I take it out of the sum, then in the sum, I can also divide by it. I have 0 on the other side, so it goes away. And then I tape these together so I don't get a short, but then I never can get the tape off. Okay, now we're getting very close. Here. Huh. Now it doesn't work at all because there's some tape left. Okay, we have only 2 more minutes to go. Anyways, maybe I jump like this. So, you know, the dni by nu I goes away, and then this is the condition. You know, is nu I for this one reaction, nu I times mu I is equal to 0. And mu I is equal to the chemical potential. That's equal to, yes? Oh, yeah. But I rather run around here and point at it. But because it's only 2 more minutes anyways. But anyways, and the mu I is the partial molar Gibbs free energy, and we know how to compute this, okay? So that's what we do then, is, now I have to, also this thing doesn't work anymore. Okay, so this is the trick now. Now we know what the mu I is these 2 terms, and I can plug this in there, and then I get 2 terms. I get the sum over the temperature-dependent part, and I leave this here on the left-hand side of the equation, the third one here with a red box. And then I get the pressure-dependent part, and I put this on the right-hand side. This is also a sum over all species. And then on the left-hand side, I replace this by a quantity that I call the equilibrium constant. You see, I define this as that term as RT times ln K. And then you see the RT goes away, and the ln also goes away. And then this equilibrium constant is just equal to this product of all the partial pressures. Okay? So this is interesting because the whole expression had a temperature-dependent part and a pressure-dependent part. And the right-hand side, which I now call the equilibrium constant, that has only the temperature-dependent parts. No pressure, right? And the pressure is on the other side. So, but the product here of all the partial pressures, where they are to the nu's power, nu is positive for the products, is negative for the reactants. So there's a ratio of the partial pressures of the products divided by the reactants. So that gives you a condition for the composition of the mixture, you know, in chemical equilibrium. And on the right-hand side is a function, a little bit complex, you know, because of all these 4 different terms that are left. But it's only a function of temperature. That's the point. The equilibrium here is only governed by the temperature. And you do have some pressure here, or in terms of the partial pressures, on the left-hand side. I mean, the partial pressure depends on the total pressure, that's clear. But, you know, the equilibrium constant is only function of temperature. That's very interesting. Okay, so so I just say this only depends on the temperature, and it gives you then, so if you have the temperature, you can compute the K. We know how to do this. I'll show you later on an approximation. And then once you have the K, it gives you a condition for the composition. And here are two examples, and maybe that's the last thing we do today. Take example number 1. A plus B goes to C plus D. So the equilibrium constant is a function of pressure and then of temperature, and it can be written like as the product of these partial pressures. So it's partial pressure C times partial pressure D divided by partial pressure A times partial pressure B. So that gives you now a condition on how much of the reaction goes to products and how much will stay as reactants. Because if you give me a temperature, I can compute K, and that's a constant now. It's a value, okay? If it's 0.5 or whatever, no, it's 1, then it means, I get equal amount of reactants and products. If it goes to infinity, if K goes to infinity, it really means everything is products, irreversible chemistry. That's what we assumed so far. And if it goes to 0, then the reaction is never going to happen, right? And the second example here is interesting because now it's not a non-equimolar reaction. Because in the first one, you see all the P0s that I have up there, they go away, okay? And the P0, what was P0 again? P0 was the reference pressure at which the entropy was defined, right? And so the second equation here, Kp now, is Pc divided by Pa times Pb. And if I want to convert that to mole fraction, so in terms of partial pressure, that's it. But there's one P0 left over, which didn't go away. And if I want to convert this to mole fraction, I need to multiply it with P squared and divide it with P. And then there's one P0 divided by P is left over, okay? So if I want to express the composition in terms of mole fraction, then it depends on pressure, okay? So the composition is not independent of the pressure. That's the point. And especially when I have non-equimolar reactions, then there's always a pressure that's left over. Okay, so maybe, let me see what comes next. Yeah, maybe we'll stop here and then continue tomorrow. Okay, so have a good evening. Remember tomorrow, no food for lunch, okay?